Well, let's see. Tips. Well, we're going to do some translating today. Maybe some of that will help a bit, but actually the percent problems are, little different phrases than the other kinds of things we've been doing. Excuse me. I'll just look at one again from my version of the homework, right? That you might have been attempting yesterday. This one says, including 10% sales tax, a new TV costs $440. Find the cost before tax. One of those that it's not just a single direct problem that what is 25% of. But I think once you do get it sort of translated, there is kind of only one calculation. So if you've added, here's where I would say, all right, it's not one of those where it's just this percentage or that percent that we're looking for, but here we have the original cost plus the 10% of sales tax. And I say, or I ask, well, what percent then of that original value are you actually paying, including the tax? All right. So kind of to figure out if you can ask yourself questions like this that kind of guide you to your equation. I'm going to pull off the sweatshirt. Can you answer that question? Do you know what I'm talking about? I paid for my TV plus 10% sales tax. What percent overall did I pay? All right, you're pausing, kind of thinking about that. Well, the original price, the whole price, all right, that's 100%. I paid the whole price of the TV plus tax. So 100% plus 10% more, you paid 110% of the original fee, original cost. Let me know if that doesn't make sense after I've explained it. Usually, oh yeah, when you say it, now I get it, but I understand how that goes. So 440 is 110% of, I was going to say of what? Of original. That's more than the original cost of the TV. Now, if I can get that far, can you write that equation, I hope? And really, that's one of those that now is in that single sentence form. The cost of the original, right? What did you pay? Maybe backing up, what is the problem asking for? Identify which concept in the problem is going to be your variable. Right? What did you pay? That's what we're looking for. Excuse me. What I highlighted the wrong part right there. Right? Did you catch that? Find the cost before tax. I highlighted my wrong sentence, incorrect sentence here. We're looking for the cost before you added the tax. So that's what you're going to name your variable. So $440 is 110% of that original value, that cost before tax. So 440 is, now 110%, gotta switch that to decimal. And you, like you said, once you get to the equation, you're okay. So, well, just working another example, something like that, getting to that point there with your equation. Dividing both sides by the 110. Just in my head, I think that's 400. Plus 10%, another 40, all right? So $400 was the original, the cost before tax. I wish I had an easy answer for you, hints for translating. Try to look for those expressions that, this idea represents the variable. These other pieces describe relationships within, between the values in the problem. And then you get a separate sort of expression for each of those relationships. We're going to see several of those today in our sort of geometry type problems, translating. Well,
Yeah, thanks. It definitely helps.
Well, okay. Thank you for, I'll keep trying for you. Yeah. But good. Thank you for bringing it up. Ask a question. That's always good. Ah, there. I'm thinking, all right, where is one more person showing up? Good. Well, our problems today, you noticed perhaps that we skipped section 3.3. I forget exactly what that was, but in our curriculum for the course, we jump right to 3.4. And these are problems that are, framed as geometry problems because they're built around geometric shapes, figures, constructions. And then we are using our translation skills to take the relationships between side lengths and so on, and plugging them into basically a formula shapes that we're hopefully fairly familiar with, to just come up with the missing side lengths or angles and triangles. We're going to talk about that a bit too. So the formulas, we're not going to actually use very many of those formulas off that formula sheet. I realize that we don't get quite as messy as some of those formulas, but we do want to understand some basic formulas for some basic shapes. Well, I start with rectangle, okay? And the first thing I would ask you is, can you write down the formula for the perimeter of a rectangle? P equals, how do I get the perimeter? What sort of mentally, you got to understand the definition of perimeter, right? What's the length all the way around? Add up the sides, right? So if we're talking sort of lengths and widths, right? We could say length, width, and add them all up, but the shortcut is 2 widths plus 2 lengths. Either order, doesn't matter, okay? Hopefully you can remember that. So here's a problem like we'll be dealing with today. I'm going to say the length of a rectangle is 5 feet less than 3 times the width. The perimeter is 110 feet. Find the length and width. Okay. Let that soak in for a second. The length, well, second last sentence, I said the perimeter, the total, right? is 110 feet. So we're going to use this formula. And there's the p-value. I know that number. I'll plug that in there in a minute. And then I have this description that describes the length in terms of the width. So really, I don't have to use the L. I'm going to put in a replacement expression that describes the length, as the sentence did, using the width. So then I really will only have an equation that has one variable, my W in it, the width. We're really kind of doing what's called a substitution. This expression taking the place of the L, the expression built out of the W. We'll do actually more of that in chapter 5, our last chapter. You'll see the same kind of problem again, really. Talk about it as a different context. So I want an expression that describes the length in terms of the width. The problem I was borrowing this from, or similar to this, would say, use W for your variable for width and write an expression that describes the length in terms of the width. Well, the length of a rectangle is. So here now is coming next are the words that are going to describe that length in terms of the width. And I might say, well, I know the length is, that's what we're coming up with, 5 feet less than 3 times the width. That's all one idea there. 5 feet less than 3 times the width. So careful with less than, you really are subtracting the 5 from something else, right? 3 times the width and 5 feet less. This is what we're trying to get you to come up with. So the length can be described as 3 times the width minus 5. That's the piece we need to put this problem together now. If that clicks, that makes sense. All right. Now I'm going to plug in these pieces into this formula. So I know 110 is the total. And there are the 2 W's to start with. And now there's 2 of these length expressions. I'm going to need parentheses because I'm going to need to multiply that whole expression times 2. Just thinking 2. Come on, hand. Take a look at that. That makes sense. There was my original formula idea. 2 widths plus 2 lengths, and there's my expression for length. Now I have an equation, looks like one of those more complicated ones near the end of last chapter. I've got to do some distributing, combining some like terms, and I can solve for the W here. Distribute 2 of each of those, right? I'll just combine those W's. Let's leave all the W's here and we'll add the 10 to both sides to cancel it out here. And I get that 120 is 8 W's. 8 times the width is 120. Divide by the 8. And I get that the W is 15. And in this problem, the context was feet. You put that in your calculator, but I kind of planned it out, worked it out ahead of time. 15 feet. Problem asks for both the length and width. What's your length? Oh, back here, it's 3 times that width minus 5, right? 3 times 15 minus 5. Turns out to be 40. 45 minus 5. The length is 40 feet. This is sort of the basis for many of the problems in this section. You have a shape, basic formula, a relationship that you work from, and then a description of how things work together. One dimension in terms of the other, so you can plug them in and build your equation. Do it again, or going to do a variation, something related, all right? Yeah, let's see. Here's a similar kind of shape, right? And the point here is that it's kind of like the rectangle, and the problem with this kind of shape would say something like, I'm fencing this field and dividing it into two sections by putting a separate piece of fencing down the middle. And the total amount of fence I want to use, and I'm going to make up some numbers and they might not work out very nice. 200 feet. 200 feet basically is your, well, you can't really call it perimeter, right? 200 feet total. That means all the four outsides plus the one in the middle, right? And then still something like the length is, I'll just make it hopefully easy, twice the width. Yeah, it's going to be a messy number. I just did a little quick mental math. The length is twice the width. You know, find the length and width. Well, rather than that basic perimeter formula that we just had, we're going to use sort of a version of it. I'm going to call it total this time instead of P. But we're still talking about lengths and widths. All right? How many lengths are there in this figure? This and this. All right, I have two lengths. But how many widths? 1, 2, 3. So you kind of have to build your own formula for this one. I'm making up here. So there's 2 lengths and 3 widths. And now I'm going to try to do the same thing I did with the basic rectangle a minute ago. The length is, length is twice the width. Well, the length is just 2 W's. Made it easy expressions for myself at the moment. And now I'm going to basically substitute that for the L in this thing that I made up over here. Now I know the total is supposed to be 200. I think if I'd chosen 210, it would be better, but 2 of these, 2 times 2W, right? The length was 2W itself, so 2 times 2W plus the other 3. Now I've got an equation with just one variable. The 200 is 4W plus 3W. See if I'd made that 210, wouldn't that be nicer? Should we do some erasure math and make it 210? Anyway, you get the point, hopefully. I divide by 7. I get that my width is going to be, what, 20 something. Bunch of decimals afterwards. I'll stop right there, 28.57 feet. And so now that I have that width, I could double it to find the length. The point of this example was kind of building your own formula based on the number of sides in the figure, but otherwise kind of basing it off of a rectangular shape, perimeter. Using the information that describes one dimension in terms of the other, come up with this sort of substitution expression that we're going to use to get down to only one variable. A couple more like that I've recognized, I've noticed are in your homework, okay? talk about them that way. There. The last couple in this section, in this homework section, are basically this kind of problem. One of them says you're going to do the same kind of thing. You're going to put a fencing around a large field, and the fencing goes up against the river. Hope your animals don't float away. But you're going to divide it into 3 sections like this. So there you've got lengths and widths again, very similar to what I just made up, but slightly different shape. You're going to build your own formula. I'll call it the total, like a perimeter again. Maybe for yourself, say perimeter, right? How many lengths and how many widths in this figure? Well, because of the river providing one side, you really only have one length. How many widths? 1, 2, 3, 4 widths. And then there would be some description, the length is 3 more than twice the width or something like that, and a total amount of fencing, just like my last example. But getting to this to start is what would be unique to this problem, and then doing that translation, 3 less than twice, excuse me for the sneeze, 3 less than twice the width. Can you write an expression for that? Excuse me. Yeah. That's what we'd be trying to come up with, say length is, sure, abbreviating, getting a funny looking L here. All right, slow down. And again, you'd have to be given a total number of sides. In fact, I'm looking at my example from the homework, and I'll just change these and make it. Is that 440 again? No, 220. And the dimensions they gave me here are 20 more than 4 times. I don't know, maybe you'll get the same relationship with different numbers, or maybe you'll get slightly different relationship, but the numbers should all work out. But the length is 20 more than addition. Well, the order doesn't matter, right? When you're subtracting, make sure that you're subtracting from probably the variable expression there. But now I have that to plug in here. And then the other 4W in my sort of made up formula. Now I would go from there. Maybe 8W, subtract the 20, 8W is 200, and what's that, 25, something like that. Just want to sort of addressing the concept of build your own formula here. And then you're doing your translation there like that. Assuming you could finish, okay? And I point out these couple in particular because they're kind of weird in the homework. This one, especially, I think it's the problem before that. Oh, we got 4 shells in there, yeah. 1, 2, 3, 4. My problem says carpenter's going to build this shelf and going to use 26 feet of board, and then a relationship between width and height, right? Height and width. And just to begin with, before I finish that up, right? Build your own little formula. Well, this total has got to be the sum of all those sides. I have 2 H's plus 1, 2, 3, 4 widths. That's what I'm getting at with this. And now, I get some relationship. The width is 11 less than 3 times the height. What's really weird about that? The width is 11 less than 3 times the height. The drawing is absolutely not to scale, because I think this is looking like a shelf like this. Like, think about that description there, really long, skinny ones. Somebody's building something like that. But you get your formula, sort of pieces put together like that, and then I'm going to plug in, and 4 of all of those. You go from there, solve, distribute, combine like terms. So there's a couple specific examples like the last 2 homework problems, I think. So as far as, given how far I think I expect to try to get today, you might find that you can get through the first 4 or 5 homework problems, and then there's going to be some weird triangle things I'm going to save for tomorrow, and then you could jump to the last 2 homework problems if you want to. Don't mind going out of order. See how far we get today. Okay, change gears a little bit. Similar kinds of constructions for these problems, though, but based on triangles. To start with, O, A, B, C. Call that angle A, angle B, angle C. If you were in a geometry class, you might notice that kind of notation describes the measure of that angle. How big is that angle? Right? The measure of angle A plus the measure of angle B and the measure of angle C. Well, these problems are based on a given value for any triangle. Those 3 angles always add up to 180 degrees. No matter how long, skinny, whatever your triangle is, the 3 angles will always add up to 180 degrees. So we always know the total. Okay? We always know the total. And now it's going to be, these problems will be similar to the ones that I just did with rectangles. For instance, there's one in there. They do this little thing in here to show you that's a right angle. What's a right angle? Well, it assumes a little bit here that, oh, everybody knows, huh? That one's 90, right? 90 degrees in a right angle. And then it says, well, this one's 32. What's the missing one? Well, that's not really even tricky expressions. These 3 have to add up to 180. Whatever given numbers you get in your version of that problem. So here I'm just doing a subtraction, right? Add those 2 together and subtract from 180, and I'll figure out what the remaining angle must be. Okay. Similar version. I'll spell this right, isosceles, right? ISC. There's one like this where they tell you these 2 are the same, and let's say this is 40 degrees, right? If they're both x's, then they're the same, right? Same size. So now I could say, oh, 180 is the 40 plus 2x. And now I can find the value of both of those. Isosceles triangle, really, this is, if you know any little bit of geometry, this would have to be an isosceles triangle. But isosceles triangle is one that has 2 equal sides. Like if this is A, that's an A. Now, those two side lengths that are the same, and it is what we call an isosceles triangle. Interesting thing, it's one of those things they prove in a geometry class. If those sides are the same, then the angles opposite are also the same, kind of like that one a minute ago, right? So that's just a little bit of geometry relationship there. But the problem that uses this expression, isosceles triangle, in your homework is a perimeter problem. So it's really how many sides? Right? It's 3 sides this time that I'm going to add up. And let's call this, I call those 2A because they're the same, right? And so I have 2 of the same plus a 3rd side. And then it goes on to give one of those descriptions. Oh, the longest side is twice the short side or something like that. So you translate those expressions, plug them in, so you end up with an equation with only one variable. And again, it has to tell you what the total perimeter is. One thing about isosceles triangles, right? I tend to draw it because it's more compact this way, where these are the 2, these are basically longer sides that are the same and then a short one on the bottom. But it could be that there's a long one on the bottom and these 2 are shorter than the bottom length, but they're still the same, right? These, I think, if I recall this problem, that's kind of what that triangle would have to look like to meet the relationships that they describe. Like the longest side is 5 less than twice the short side or something like that, or that can't actually be. I won't try to go into that. If I say this one is shorter than those 2, well, that physically it can't happen. Twice the short side, the long side's always got to be longer than the sum of those 2 sides. That's, again, just a geometry thing. It won't come into play. You don't have to worry about it. This is what you need to be able to do, is build your own little formula. All right, this one's about perimeter. Couple based on this idea that the sides of the triangle, the angles of the triangle all add up to 180. Okay. And well, I think we have, how are you doing with that stuff? Did I present enough? Yeah. Can you do one more specific or something? No.
Can you do the one with the 90 degrees, like that formula?
Yeah, okay, let's see. Like the very first one I did up here a minute ago, the one I had up here, huh?
Yeah.
I think this, if you look at your homework, that might be like the very first homework problem. I drew this and said that was 90 degrees and this was 32. That one?
No, it's like the formula like adds up to 90 degrees.
Oh, there's one in there that adds up to 90, huh?
Is there?
Well, you could say it does, I guess. What's he talking about? I guess, huh? And I'm not sure if maybe you're seeing something else someplace, but if they all add up to 180, well, 90 is half of that, right? You know that one's 90, well, these other 2 are going to add up to another 90. I'm not sure if that's maybe where you're coming from, but no.
Because I remember in geometry, there's like a formula where it like adds up to 90. Like, you know what I mean? Like 90 is the sum.
Uh-huh. Well, and I don't think these are in our mom problems this chapter. I was looking, I thought I tried to look through those and make sure, but that's all right. Whoops. Just a couple geometry concepts. Maybe this is what you're thinking of. Here's, I'm implying this is a 90-degree angle, right? If I have 2 angles that add up to 90, Those are called complementary angles. Does that sound like something you're looking at? Well, you know, two angles that add up to 90. One, if I know one is 2 times the other, you know. Well, now I could say the A is actually 2B plus B. I have 3 B's. This must be 30, and that's twice that is 60, something like that. A straight line, this total is 180 degrees. Like, you're going to turn 180 degrees. You probably use that expression someplace rather than going all the way around 360. So these are two angles that add up to 180 are called supplementary. I wasn't really planning to address that just because I didn't really see that kind of concept in our homework problem, but you know, it's not unusual information to have. Can you give me an idea where that's coming from, that you're finding that problem? Was it in the mom homework?
No, it was just kind of like, since we're talking about like angles and degrees, I remember it from like geometry, like way back then. I was like, isn't there a second equation that adds up to 90?
Yes, well, this might just be the sum of two angles that add up to 90. Those two angles are called complementary. And if they add up to 180, those two angles could be supplementary, or if they all add up, I suppose you could pick any arbitrary angle and say, these angles all add up to this number, as long as I have a relationship between them. Maybe it's even in our text. I was perhaps addressing more specifically the kind of problems that we were going to pull from that and ask you to do. I'm going to ask you, if you run into that specifically, if you could send me that question maybe in the forum, I could reply to that.
Okay.
Okay. Sorry to not be more direct here. I was thinking we have okay amount of time that start this other, might say the other big idea in this section. Again, I did schedule 2 days for this topic. Maybe kind of a light day tomorrow. I just show up with questions, difficulties you're having. All right. Now this one, maybe you've heard something about this. I'm sorry, I couldn't tell who was asking that question a minute ago about 90 degrees. But maybe this is what was related to what you were thinking of, okay? But here's a right triangle. That is a triangle that has a 90-degree corner in it. Right? So this concept only applies to right triangles. And it's called the Pythagorean theorem. Now, a theorem is like a mathematical rule that's been proven. And it's been proven enough that we accept this concept as true, as you know, it exists, it's true. And Pythagorean, it's named after a Greek mathematician, Pythagoras. Greeks did a lot of early work with the math that we use, especially geometry. I think he was something like 1200 BC, something like that, he lived. And they almost had like, you know, cult-like organizations around math, making all the numbers work out really nice. So he developed this formula about relationships between the sides in a right triangle. So usually this is described with letters like this, side lengths. We're talking about the lengths of these sides, okay? A, B, and C. And these two, right, the ones that make the corner are referred to as the legs of that triangle. And this one, the special one, is the diagonal, right? Hypotenuse. You might have heard that word, wondered what it is. A hypotenuse is that diagonal. And there's a special relationship in any right triangle between the legs and the hypotenuse. So you always have to, this is the important one to remember. it's this, the diagonal is always the side across from the right angle, all right? You got to know which sides are which. Even like that one I drew a minute ago, let's see if I can kind of do it again, where there was the right angle, right? So this is your hypotenuse down there, right? The diagonal. Probably going to be the longer side, actually. Okay, so the formula, the theorem says, and you can actually sort of interpret it geometrically. If I square the side length A and I square the side length B, that equals what I get if I square side length C. Wow, really? Why? Geometrically, you could interpret it as I build a square, when I build a square, those two areas are going to add up to the area of a square I could build over here. Wow, interesting, neat. If you know two of the sides of a right triangle, now you could use the formula to find the missing side. I'm going to get this one out of the way here, okay? So how does it work? Well, let's say I know that B equals 4 and B equals 7. Let's find side length C. So I'm plugging A and B into this formula, and C is the one on the opposite side. In this case, I'm looking for the hypotenuse length. The hypotenuse is always the one that's alone on the one on the other side. That's important. The hypotenuse is always the value alone over there. So this is saying 4 squared plus 7 squared equals C squared. Eventually, I want to find out what's C, not C squared, but just C. Okay, so let's see. Let's put that in my calculator, but 16 plus 49. And what is that? 5965. Notice that you square each one individually, right? You don't do 4 plus 7 is 11 squared. That's 121. Much different number. Right? Square each one separately, then add them together. Now I've got 65 is C squared. Well, I want C. How do I find C? If I take square root, remember those kinds of numbers we talked about? What number can I square to get this thing? If I square root something squared, that just gives me the C. It's like the opposite operations, like multiply, divide, add, subtract. I can square something, and going backwards is square rooting it. And that's, you need something on your calculator for that. And that will mean what I really want to do is find the square root of 65. Now, we're going to have to get a decimal approximation. I'm going to arbitrarily say, let's use 2 decimals right now, 2 decimal places. But what perfect square number is that real close to? Can you think of that? What number can I square and get real close to 65? You know, 5 is square root of 25, 6 is 36, 7 is 49, 8 is 64. So the square root of 65 is going to be a little bit more than 64. That's what we expect to get out of our calculator. Now, calculator. Hope you got that handy. All right, let's talk about that for a second. And I'm looking at mine. Yes. Now mine, one of these fairly simple ones, but every one of your calculators has got this on there someplace. Now down the left-hand side, we've already talked about, there's my pi button on my calculator. And a little farther down, there's actually one that says x squared. I think I referred to that. If I were to say like type in 5 and then push that button, it would automatically square it and turn it into 25. It would square it. But most all of my buttons on my calculator have a second function. there's a second thing they can all do. If I push the second button, and then I have to look for the little other thing that that button will do. It's usually a lighter color just up above the button. The x squared button does the opposite if you push the second. It squares as the main function and it square roots as the second function. So I want to use the second function of that button. I'm just going to do this right now with this one. Make sure I'm going to push second square root, and it gives me a symbol that looks like this, the square root sign, and a parenthesis waiting for me to put in the number I want. I'm going to type in the 65. I think if I don't have anything else going on, I could just stop, but closing the parenthesis, there's a parenthesis button up there. You could close the parenthesis. But, yep, I got 8.06. All right, so we're doing a couple things. One, using our calculator to come up with square roots. And then we'll, once we all are sure you're comfortable with that, we'll come back to using this formula again. Is everybody able to find that square root function on your calculator? I hope so. Let me know if you're having trouble. Again, that's kind of thing where, depending on the kind of calculator you have, it might be hidden somewhere else. But often it is related to the x squared button, which you might have on your calculator. So it wasn't an exact value. In fact, it's likely to be an irrational value. That decimal probably goes on and on and on forever. We have to agree to round it off someplace. But that means 4, 7, and a little more than 8 are the sides in that triangle. Do it again. How am I doing here? Yeah, good. Oh, well, we're about out of time, huh? I'll do one more, but we'll come back and do more of that. Maybe 2 more. Hopefully it's obvious in the drawings that you're given, even if you're not given the drawing, which corner is the right angle so that you can identify the hypotenuse. There are some of these in this problem that talk about, oh, my 16-inch TV. TVs are always measured in diagonal. What's the diagonal distance? It means you know the hypotenuse in that kind of problem. What are the length and width? We'll get there in a minute. So here's similar idea, right? I know an A. Notice I don't really even need the A's as long as the letters, as long as I know that's the hypotenuse. I can put those letters in myself anyway. Six squared, 8 squared, make sure that you remember to square them individually. And I made up easy numbers here for this one. Add them together and I get 100. Maybe you can do that one in your head. What number can I square to get 100? But you just want to practice, play with your calculator. Square root function, second function, type in 100, and it tells me, oh, that means the C must be 10. A nice integer whole number value. When you get nice integers like that, nice whole numbers, they have to be whole numbers, right? Physical dimensions are all going to be positive. When you get nice whole numbers like that, they're referred to as Pythagorean triples. They work out exactly nicely, nice numbers. And there's quite a few of them out there. This one is an example. I doubled them all, but 3, 4, 5 is probably the most common example. And you notice this is like what we call similar triangle, twice the dimensions, twice the 3, twice the 4, twice the 5. That's how I was able to make that up on the fly like that. One more, in case you want to keep working on homework, kind of related to the one down here. And let's say I have one like this. What's different about this drawing? I know the hypotenuse, I'm looking for one of the legs. All right, I'm still using the same basic formula idea. What's important is that hypotenuse number is the one that's always alone over there. So the 25 goes over here. A is what I'm looking for. And there I plugged in my B. So that's what's different about this version. I'm looking for the side length, not the hypotenuse. And so here, 15 squared, I think is 225. I do this enough, I know those numbers. 625 for that one. All right. Can I make nice numbers for myself? That might be nice. Well, what I got to do now? What do I have to do? I have to get the A's alone. I have to subtract that. I think that's 20. 20 times 20. Oh well. But so now I have to find the square root of both sides. Really, you could say, oh, now I'm going to square root both sides, and that's going to say A equals square root of 400. And I got a 20. Watch out for units that might be in the sort of word problem type context for these few Pythagorean theorem problems. There's 4 or 5 of them in there. You'll expect 1 or 2 on your test for this section, maybe only 1. So I'm trying to think. 3 times 5, 4 times 5, 5 times 5. I made up numbers and it was still a version of the 3, 4, 5. That's why it worked out so nice. I got lucky. I made it up. I just did want to present that one before we finish today that showed that you could be trying to find one of the legs sometimes. And then we had to do a subtraction in order to get there. Well, give those all a try. Do your best translating those expressions. I'll watch for difficulties or questions you might send me, and we'll pick up where we left off here and do more of it tomorrow. Okay? Okay. Thanks, folks. Good luck.